The universe is vast. It's a place of breathtaking beauty and unimaginable scale. When we gaze up at the night sky, we are looking back in time. The light from the nearest stars has traveled for years to reach us. The light from distant galaxies has journeyed for millions, even billions of years. But we can look back even further than that. We can see the faint residual heat left over from the very beginning of everything. This is the afterglow of the Big Bang, a baby picture of our universe. And in this picture, there is something strange, a cold, lonely patch that just shouldn't be there. This is the cosmic microwave background cold spot, and it challenges everything we think we know about the cosmos. This isn't just a slightly cooler region, it's a profound anomaly. It's a blemish on an otherwise remarkably uniform canvas. Science has built a fantastic model of the universe, one that explains its evolution from a hot, dense state to the sprawling web of galaxies we see today. But the cold spot is larger and colder than virtually any prediction allows. It stands out like a single blue marble in a vast sea of red ones, making us question the rules of the game itself. To understand the cold spot, we must first understand the light in which it was found. This light is called the cosmic microwave background, or CMB. It is the oldest light in the universe, an echo of the Big Bang. For the first 380,000 years after its birth, the universe was an incredibly hot, dense soup of particles and radiation. It was so hot that atoms couldn't form. Everything was a foggy plasma. Light was trapped, bouncing endlessly between charged particles like a ball in a pinball machine. But as the universe expanded, it cooled. Eventually, it became cool enough for protons and electrons to combine and form the first hydrogen atoms. Suddenly, the universe became transparent, and the light was set free to travel across the cosmos forever. This ancient light has been traveling for 13.8 billion years. As the universe has expanded, the wavelength of this light has been stretched out, shifting it from visible light into the microwave part of the electromagnetic spectrum. In the 1990s, the Cosmic Background Explorer, or COBE satellite, gave us our first detailed map of this radiation. It showed a universe that was almost perfectly uniform in temperature, but with tiny, minuscule variations. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP. Its mission was to create a far more detailed map of the CMB, to study those tiny temperature fluctuations with unprecedented accuracy. And as scientists processed the data and the new, sharper image of the baby universe emerged, they saw it. There, in the direction of the constellation Eridanus, was a region of the sky that was significantly colder than its surroundings. What makes the cold spot so strange isn't just that it's cold. The entire CMB map is a patchwork of slightly warmer and slightly cooler regions. These fluctuations are incredibly important. Without them, the universe would be a uniform, boring soup. The tiny, denser, slightly warmer spots had enough extra gravity to begin pulling in more matter, eventually forming the stars and galaxies we see today. The standard model of cosmology predicts the size and temperature distribution of these spots with remarkable accuracy. The cold spot breaks these rules. Firstly, it is enormous. It stretches over 1 billion light-years across. If you could see microwaves and you held your hand up to the sky, the cold spot would appear about 20 times larger than the full moon. The probability of such a massive cold region forming by pure chance, according to the standard model, is incredibly low. Some estimates put it as low as 1 in 1,000, while others suggest it's closer to 1 in 50. Secondly, there is the issue of its profile. It isn't just a single large cold area. It has a complex structure with an even colder spot nestled inside a larger, less cold region. When faced with an anomaly, a scientist's first instinct is not to invent new physics. It is to question whether the existing physics, stretched to its limits, could account for the observation. The simplest and perhaps most likely explanation for the cold spot is that it is just a statistical fluke. It is an incredibly rare but perfectly possible arrangement of matter in the early universe. Our universe is a big place, and in any random process, no matter how unlikely, extreme events can and do happen. Someone, somewhere, will eventually win the lottery, even though the odds are stacked against them. The standard model of cosmology is based on randomness. When we run computer simulations of the early universe, we essentially roll the cosmic dice over and over again. But if you run enough simulations, thousands upon thousands of them, you will eventually generate a map that includes a feature that looks very much like the cold spot. The problem with the cold spot is that it lies in a gray area. The odds, estimated to be somewhere between 1 in 50 and 1 in 1,000, are low enough to be suspicious but not low enough to definitively rule out chance. This idea is scientifically sound but perhaps a little unsatisfying. It's like finding a mysterious footprint on a deserted island and concluding that it was probably just an odd-shaped rock. Now we venture into the truly mind-bending possibilities. What if the cold spot isn't a feature of our universe, but a feature imposed on it from the outside? This is the basis of one of the most exciting and speculative theories about its origin, that the cold spot is a bruise, a scar left behind from a collision between our universe and another. This idea comes from a branch of theoretical physics known as string theory, which allows for the existence of multiple universes, or a multiverse. In this picture, our universe is just one bubble floating in a vast cosmic ocean, alongside countless other bubble universes. According to this theory, these bubble universes aren't necessarily static. They can drift through this higher dimensional space, and occasionally, they can bump into each other. What would such a colossal event look like? It wouldn't be an explosion in the traditional sense. Instead, the collision would send a shockwave of energy rippling through both universes. This impact would quite literally knock some energy out of a region of our universe, leaving behind a permanent mark. As our universe expanded and cooled, this bruised region would manifest itself as a large, unusually cold spot in the cosmic microwave background. This is a breathtaking concept. It suggests that the cold spot is a fossil, a remnant of a dramatic event that predates even the formation of the first atoms. It would be the first tangible piece of evidence that other universes exist. The theory even makes specific predictions. A cosmic collision should leave a particular signature on the polarization of the light within the cold spot. It wouldn't just be colder, the light waves themselves would be twisted in a specific non-random pattern. Finding such a pattern would be a smoking gun, elevating the multiverse from a mathematical curiosity to an observed reality. Of course, this is highly speculative. There is currently no direct evidence to support the idea of a multiverse, let alone a cosmic collision. The thought that we might be able to see the imprint of another universe on our own sky is one of the most profound ideas in all of science. It would fundamentally change our place in the cosmos, revealing our universe to be just one island in an infinite cosmic archipelago. There is another, less exotic but equally fascinating explanation for the cold spot. It suggests the anomaly isn't a feature of the early universe at all. Instead, it might be an illusion created by something in the more recent local universe. The idea is that the cold spot isn't intrinsically cold. Rather, the ancient light from the CMB is losing energy as it travels through a vast, empty expanse of space on its way to us. This expanse is known as a supervoid, a region of the universe that is unusually barren of galaxies, stars, and even dark matter. How can a void make light appear colder? This is due to a phenomenon called the integrated Sachs-Wolf, or ISW, effect. In an expanding universe, light gains a tiny bit of energy as it falls into the gravitational well of a large structure, like a supercluster of galaxies. It then loses that energy as it climbs back out. If the universe weren't expanding, this would cancel out perfectly. But because the universe is expanding, and that expansion is accelerating, the structure has stretched out a bit by the time the light is climbing out. The opposite happens when light travels through a void. As light enters the void, it has to climb a small gravitational hill, which causes it to lose a little energy. But because of cosmic expansion, the void has become larger and emptier in the meantime, so the light doesn't regain all the energy it lost. In 2014, astronomers mapping the distribution of galaxies in the direction of the cold spot found something remarkable: a colossal supervoid. It is one of the largest structures ever discovered, spanning some 1.8 billion light-years. With several competing theories on the table, the job of the scientist is to act as a detective, gathering evidence to determine which one is most likely to be true. Each theory makes slightly different predictions. First, let's consider how to test the supervoid theory. If the cold spot's temperature is caused by the ISW effect as light passes through the Eridanus supervoid, then the effect should be calculable. However, when they run the numbers, a problem emerges. The supervoid, as vast as it is, doesn't seem to be empty enough to account for the full temperature drop of the cold spot. It can explain some of the coldness, but not all of it. Next, how do we test the multiverse collision hypothesis? This is trickier as it involves physics we don't fully understand. However, a cosmic bump should leave a specific swirling pattern in the polarization of the CMB light. Scientists are using telescopes like the Planck satellite and ground-based observatories in Antarctica to meticulously map the polarization of the CMB across the entire sky, paying special attention to the cold spot, looking for that telltale signature. Finally, what about the statistical fluke idea? This is the hardest to disprove. We cannot simply rerun the Big Bang to see if we get a different result. Instead, we must rely on improving our statistics. The story of the cold spot is far from over. In fact, we are entering a golden age of cosmology, with a new generation of telescopes and surveys poised to provide the data needed to solve this and many other cosmic mysteries. Projects like the Vera C. Rubin Observatory, the Euclid Space Telescope, and the Nancy Grace Roman Space Telescope will map the positions and distances of billions of galaxies, creating a three-dimensional map of the universe's structure of unprecedented scale and detail. This data will be the definitive test for the multiverse collision theory. If the predicted polarization patterns are there, it will be a revolutionary discovery. If they are absent, it will deal a significant blow to the idea. The cold spot is more than just a curious anomaly on a map of the sky. It is a profound reminder that the universe does not always conform to our expectations. It is a testament to the power of scientific inquiry. If it turns out to be something more, the implications are staggering. The discovery of a scar from another universe would be a turning point in human history, transforming our universe from a unique, solitary existence into one member of a vast, perhaps infinite cosmic family. And so we look up at the sky with a renewed sense of wonder. The cold spot invites us to be humble, to admit that there is much we do not know. It encourages us to be bold, to imagine possibilities that stretch the limits of our minds. Whatever the answer may be, the quest to understand this one cold patch in the heavens continues to drive us forward, deeper into the beautiful, magnificent, and wonderfully mysterious universe we are privileged to call home.